For decades, computing relied on the execution of rigid binary bits. Today, operations revolve around the token, the fluid fragments of meaning through which artificial intelligence constructs sequences of thought and reasoning. Traditional enterprise data centers were architected to prioritize a specific objective: storing static information and retrieving it upon request. Generating tokens requires a different operational footprint. Facilities are evolving into AI factories, sites optimized for the continuous manufacture of digital intelligence rather than simple data storage. This transition necessitates a comprehensive redesign of the computing stack, starting with the physical silicon and extending to the governance frameworks used to manage it. The drive for this redesign follows the evolution of the software. AI has moved beyond passive chat interfaces and is now deploying as autonomous agents that interact directly with physical environments. To understand the stakes of this transition, we must deconstruct a modern AI deployment, analyzing the hardware, the software abstraction layers, and the governance protocols that ensure its reliability. We can ground these concepts by looking at a primary deployment target for modern AI, a digital twin managing a complex industrial environment. This is a high-fidelity digital replica of an industrial logistics warehouse. The entities managing the sorting, routing, and heavy machinery in this space are not running on pre-programmed scripts. They are agentic systems reasoning their way through a physical simulation. An AI agent perceives its environment, identifies immediate problems, plans a sequence of actions, and executes actions using specialized tools. When these agents move from simulations into $100 trillion global supply chains, hardware failures or logic errors result in immediate physical consequences. Securing these agents requires looking past the simulation and examining the real-time compute engine powering their decisions. Beneath the digital twin lies the physical infrastructure that makes continuous simulation possible. Historically, AI development was limited by the pre-training phase, where massive datasets were processed to teach a model basic patterns. Current scaling follows three distinct laws. Pre-training was simply the first constraint. The second law is post-training scaling, where models are refined through fine-tuning and synthetic data. The third law, inference, now represents the largest demand on computing resources. This demand spikes because agentic models do not simply provide a one-shot answer. They allocate compute to explore multiple alternatives in real time before committing to a physical action. This continuous reasoning loop can require 100 times more processing power than a standard AI query. The Blackwell architecture and the Dynamo operating system were designed to manage this specific load, orchestrating test-time scaling across unified server racks. While hardware scaling provides the raw capacity for an agent to reason, specialized software layers are required to translate that capacity into industrial tasks. Raw compute power is ineffective if developers cannot easily apply it to specific industrial problems. A software acceleration layer bridges the gap between silicon and the application. Libraries like CUDA-X abstract the complexity of parallel processing, allowing developers to focus on specific agent behaviors, like route optimization or weather modeling, without managing underlying hardware memory. For deployment, enterprises utilize NVIDIA Inference Microservices, or NIMs. NIMs package reasoning models and their dependencies into secure containers that can be deployed across a company's existing network. Enterprise IT departments now onboard and manage these digital agents with the same rigor traditionally reserved for human personnel. As this digital workforce integrates into infrastructure, the enterprise inherits new risks that require oversight beyond simple code-level guardrails. We must look at the software's physical impact through the lens of national and systemic risk management. When autonomous agents control electrical grids or manufacturing robots, the primary risk moves from digital data loss to physical safety. In our warehouse simulation, the robot's physical actions must align with strict institutional safety requirements. Trustworthy deployment is defined by the core functions of the NIST AI Risk Management Framework. The MAP function requires operators to formally identify the risks inherent to an agentic system operating within a specific physical environment. The measure function focuses on evaluation, scoring the agent's reasoning against verifiable safety and bias thresholds. NIST is currently developing a specific critical infrastructure profile to guide operators in applying these practices to physical AI-enabled systems. The high compute capacity of the AI factory allows an agent to run these compliance checks in real time, verifying its own safety logic before executing a physical task. This framework provides the architectural constraint necessary to make autonomous infrastructure physically and legally viable. This 3D stack represents the complete architecture of industrial AI: hardware compute at the base, software abstraction in the middle, and risk policy as the governing envelope. Industrial facilities now function as active manufacturers of intelligence, moving beyond the static data retrieval limits of the previous decade. The AI factory has become the foundational infrastructure required to operate in the modern global economy. Managing the next phase of the Industrial Revolution requires scaling raw compute power while simultaneously building systemic trust. An autonomous system provides no value without the mathematical certainty that it will act safely. Mastering this transition requires uniting high-performance hardware scaling with rigorous risk governance to build autonomous systems that are both capable and trustworthy.